Hey, welcome back to Fat Mama Physics. In this video, we're going to do more examples of Feynman diagrams. On to example 4, I'm going to do A, B, C, and D all in one go. Using the diagrams involving the W boson and 2 quarks or leptons given on your cheat sheet, we probably may not need that. We want to draw the Feynman diagrams to represent the following processes. So, we have a reaction here. So usually the first thing I like to do when I get when I have to draw a Feynman diagram is to look at each of these particles and to see what could be potentially happening. So here we have a muon, and the muon, this is the particle itself, not the antiparticle. Okay, it starts off with a negative charge since it is in a lepton. So this is a lepton. Here with an electron, this is also a lepton. This is a lepton, and that's a lepton. So we can double check here. We have one antiparticle, and here we have two just regular particle. So notice that these are leptons being involved, so no quarks. The next thing, now that I know that there are just leptons, I kind of want to check for a lepton conservation. So a lepton number conservation. So we do have here a +1 lepton number. We have another +1 here. And then this will be a -1 since this is an antiparticle, anti-lepton, and this is +1. So it looks like lepton number is conserved. We also want to check for lepton family number conservation. And what that means is our leptons are grouped into either the electrons, the muons, and the taus. So each of these have also lepton numbers associated with, we call the electron lepton family number, and then the muon family number, and then the tau. So we'd also want to do the same thing with those. So a lepton number of +1 for the particle and a -1 for the anti-family lepton particle. So in this case here, we see this is a group. Okay, this is a group because here we have an electron with a +1 electron family lepton number, and then here we have a negative lepton family number. So these two, so this will give a net 0 for the electron lepton family number. I'll probably mix it. But then the mu, since we have one for the reactants and then one for the products, or this is one for the reactants, that one for the products, that we know the muon family number, lepton number is also conserved as well. Okay, so we also see that the fact that we have a antiparticle-particle pair here produced. So that is a possibility, knowing that we only have this one lonely muon to start off our reaction with. So it seems like what is happening is this muon is going to turn into an muon neutrino. In the process, it will emit an exchange particle, which then becomes an electron and neutrino. So it looks like some sort of decay is happening. Okay, and so with decay, usually we know that the exchange particle involved is going to be the weak interaction ones. So so probably your W and the Z bosons. Okay, so let's start. So that's the stuff that I want to think about before I even start my Feynman diagram, which is think about what is potentially happening and seeing what's conserved, not conserved, what could be turning into what, etc. So I'm going to draw A up here. So we started with our muon, which is U-, and it's going to come here and it's going to leave as a muon neutrino. These are both the actual particles. These are not antiparticles, so I'm just going to draw arrows going forward in time. Let's draw this one a little bit back. This is going to produce a W or Z boson of some sort. So I'm going to draw a squiggly line, and what is produced is my electron anti-neutrino pair. So here we have my electron. This is my electron anti-neutrino. This is an antiparticle with the arrows pointing backwards, a regular particle, arrow pointing forwards. Okay? So the next question is, okay, so what is possibly mediating this exchange? So here we have an electron coming out, which has a -1 charge. So potentially we have a minus boson, W boson coming in, which will be the exchange particle, and we can just double check this one. Our muon has a negative charge, and it becomes it becomes a neutrino, which has a 0 charge. There has to be a minus charge that leaves this junction, which can only be a W minus boson. So that conservation at this junction checks out. Over here, we also have this negative boson, W boson, becoming the electron particle, and the anti-neutrino here has no charge. So W minus works out. Okay, next up, we're going to draw B. Oof, we're running out of space here, so I'm going to make this guy smaller. Okay, so drawing B, all right, so again, it's the same processes. I'm going to look at this particular reaction first and identify my pairs. So it looks like this is a pair here. Okay, with an electron and its anti-neutrino pair. Here we have a muon and its anti-neutrino pair. Looks like we have a net 0 for the lepton number and for the lepton family number. It almost seems like that the first two particles are annihilating one another, and then it gives off some exchange particle, which then produces another particle-antiparticle pair. So if we draw that out, the electron and the anti-neutrino coming in together, the electron is going to move forward, and the anti-neutrino, the anti-electron neutrino is going to go backwards since it's an antiparticle. And it looks like it's going to produce this muon pair here. So we have the muon and its antiparticle. And again, since we have a negative charge here, after it annihilates, it has to become a minus W boson, because at this junction we need a negative charge leaving, and this junction we need a negative charge going in. So it has to have, our exchange particle has to have a negative charge, which is the W minus boson. Okay? Alright, so let's move on to the next one, which is going to be C. So C, we have potential quarks that are involved. So this question tells us the quark structure of positive pion, which is U and then D, the anti-D. It's a meson, so it has no baryon number. And it also could be produced through an anti-particle-particle pair production. Or it can annihilate. That could happen too. So let's see what is produced. Oh, hey, look. It's two leptons that are being produced. Okay? So two leptons being produced. They are in fact the anti-particle-particle pair, since a muon plus would be an antiparticle. So it looks like there is no quarks in the products. So because there is no quarks in our products, it is likely that these two quarks inside the pion annihilated one another, producing an exchange particle, which then produces these lepton pairs over here. Okay, so drawing that, we're gonna have U, we're gonna have D. They're going to come together, and the D here is an antiparticle, so moving backwards in time. They're going to produce probably some squiggly line here, and they're going to produce the two new leptons, which are mu plus and anti-neutrino for U. This one is the particle, this is the antiparticle. And notice that in this case and for the previous cases, lepton family number has been conserved, since this is plus 1 for the neutrino and -1 for the anti-neutrino mu. Same thing for the previous ones too. They've been just annihilating one another. In this case, we want to analyze the charges. We have the to figure out which boson is the mediator exchange particle. Well, it looks like we're going to have a positive one. So, yes, it does seem it's going to be the W+, but let's just confirm with the the pion plus. The up quark has a charge of positive 2/3. The anti-down quark normally would have negative 1/3. Since it's the anti-quark, this will have a positive 1/3 with a total combined charge of plus 1. So having a +1 charge coming in and a +1 charge moving out, the mediating particle needs to have a positive charge, which will be the positive W boson here. Okay. All right. The last one, D. D is a kaon. And afterwards, it looks like it's going to produce this lepton pair again. So it's a muon and its antiparticle, the anti-muon neutrino. And the kaon is looks like it's got a strange quark and an anti-up quark. So it looks like a decay, some sort of happening, since the strangeness is not conserved, since we've lose a strange quark in our products. So we don't have any quarks in our products, so it looks like these two quarks are annihilating one another, producing this lepton pair. So let's draw that again. It looks very similar to C. Okay, strange is a particle antiparticle for the up quark. It's going to produce some boson, and it becomes a this is a muon, which is a particle, and its antiparticle, the anti-mu neutrino. The mediating particle seems to be the W minus boson because it's the negative charge. We have a net negative charge in our products. And so the only thing so we need a negative charge coming into this junction, which is the W minus boson. Checking with our reactants, we have the strange quark, which has a negative 1/3 charge. Anti-up normally would have 2/3, but since it's the antiparticle, this is negative 2/3. Added together gives us -1 coming in, which then needs to be mediated by the negative boson. Okay, negative W boson. So there you go. The conservation charges check at these two junctions. We are done with D. This is example 4. So we have example 6 and 7 to go. All right. So there we go. Hopefully this wasn't too bad. And I noticed a lot of these examples are very similar. So hopefully you get a better sense of how annihilation and pair production works after this. So I thank you for watching. I wish you good luck. Fab Mama Physics signing out.